Hello, welcome to this lesson. In this lesson, we will discuss some basic theorem in recurrence relation, and after that we solve an example. Okay, so this is the theorem. If y of n, okay, you choose a function y of n, okay, then the forward difference of y of n is, let's represent the forward difference of y of n to be what? V of n. Okay, so if the forward difference of y of n is denoted by v of n, then the sum of v of r as r starting from m up to n is given by y of n plus 1 minus y of m. Okay, let's prove this theorem. Now we know that our forward difference of y of n is given by v of n. Then from definition, our v of n will be given by y of n plus 1 minus y of n. Then from here, we are trying to prove this theorem. So we will find v of n up towards v of what? M. Okay, so we are done with v of n. So the next one, the previous term will be what? V of n minus 1. So v of n minus 1 is the same as y of n minus 1 plus 1 minus y of n minus 1. Okay, but y minus 1 plus 1 is what? 0. So therefore we get y of what? N minus y of n minus 1. Okay, that's what we have here. Now v of n minus 2 will be y of n minus 2 plus 1 minus y of n minus 2. But n minus 2 plus 1 is what? N minus 1 minus 1. Okay, so v of n minus 3, we will get this. Okay, we can't list all of them, so let's find v of n plus 2. V of n plus 2 will be v of n plus 2, y of n plus 2 plus 1, which is y of n plus 3 minus y of n plus 2. Okay, y of n plus 1, we get this for y of n plus 1, v of n plus 1. Then finally, v of m is given by y of n plus 1 minus y of m. Okay, so now let's try to simplify it. So we find the sum on both sides of the equal sign. Okay, so the sum is given by vm, okay, plus v of m plus 1 plus v of m plus 2, okay, up to v of n minus 3 plus v of n minus 2 plus v of n minus 1 plus v of n. Okay, so we are finding the sum on the right hand side, on the left hand side of the equal sign. Okay, so we can write this in a compact form. Okay, and we can write this in a compact form using the sigma notation. Okay, so this is the compact form. That is v of r as r starting from m up to n. It means that when you expand this, you will get the first term will be v of m, which we have here, then plus the next term will be v of m plus 1 plus v of m plus 2 up to v of n minus 3 plus v of n minus 2 up to what? V of n. Okay, so this is the same as this. Okay, now let's consider the right hand side. So we are finding the sum on the right hand side of the equal sign. Okay, so we have y of n plus 1 minus y of n plus y of n. We realize that this minus y of n and this also plus of y of n. Okay, so this cancels out. Also this minus y of n minus 1 and this plus y of n minus 1. This also cancels out. This is plus y of n minus 2. This minus y of n minus 2. It also cancels out. So all of them, you realize that they will all cancel out. Okay, you see, they will all cancel out. We have minus y of n plus 2, positive y of n plus 2, minus y of n plus 1, positive y of n plus 1. Okay, so you realize that all of them will be cancelled, leaving only what? Y of n plus 1 up to what? Minus y of m. Okay, so that is, we get y of n plus 1, that's what we have here, then minus y of m. Okay, so this is a proof of the theorem. Now let's use this theorem to solve one basic example. Then in our next lesson, we will also look at some other examples. Okay, so this example is on exponentials. Okay, so we choose y of n be equal to a exponent n. Then from definition, our forward difference of y of n is given by this. Okay, therefore the forward difference of y of n, where y of n is an, can also be written as the forward difference of an, since yn is what? The same as an. Okay, then y of n plus 1, so we just replace this n by what? N plus 1. Okay, so when we do that, we get a exponent n plus 1 minus y of n, that's what? A of n. Okay, and this is the same as what? A dot a, or a times a to the power n minus a to the power n. We factorize a n out, then we make a n the subject. Okay, so we divide 2 by a minus 1. A is what? A constant. Okay, a is a constant, so a to the power n is the same as this. Okay, now let's find the sum on both sides of the equation. Okay, so when you do that, we introduce a dummy variable r, so that when you find the sum as r starting from what? We find the sum on both sides of the equation. Okay, so that's r starting from m up to what? N is the same as this constant. Okay, this term, this is what? Constant. So we can bring it out of the sigma notation sign, since summation is a linear operator. Okay, so we bring the constant out. Okay, now from definition, or from the term that we discussed, you see, when you have summation of the forward difference of y as r starting from m up to n is the same as y of n plus 1 minus y of m. Okay, so now it means that this term, the summation of the forward difference of ar as r starting from m up to n, is given by this. Okay, so we obtain this equation, and we can rewrite this as what? As that. So therefore, the summation of a exponent r as r starting from m up to n is given by a exponent n minus a exponent m, or divided by a minus 1, where a is a constant. Thank you so much. In our next lesson, we'll solve some other examples.